In this video, we are going to learn what happens when we add another polarizing filter to our transmitted light microscope. We will be learning about interference colors and birefringence. To do this, we first need to insert our analyzers. Here, I turn the switch above the objectives labeled A. Switching this on inserts the second polarizing filter at an exactly perpendicular direction to the existing polarizer. We call this cross-polarized light. Here I go from plain polarized light to cross-polarized light. The colors that you see now are known as interference colors. Interference colors are the observed colors under cross-polarized light only. In cross-polarized light, notice that as I rotate the stage a full 360 degrees, that the interference colors fade to black exactly 4 times. These are known as extinction positions and occur 90 degrees away from one another. We call these anisotropic minerals. This is another example of a grain mount in plain polarized light. Notice how it is colorless and transparent. When I switch to cross-polarized light, this mineral does not let any light pass through, even as I rotate the stage. Some minerals are extinct at all orientations, meaning they never display interference colors. We call these minerals isotropic. In summary, anisotropic minerals have 4 extinction positions in 360 degrees of rotation and display interference colors in cross-polarized light. Isotropic minerals can be transparent in plain polarized light, but never let light pass through in cross-polarized light. Now let's try and calculate birefringence. Birefringence is a property of anisotropic materials. As light is transmitted through materials, the light ray splits into 2 rays, a slow ray and a fast ray. Here we have the Michel-Levy chart, which is used to calculate birefringence. Along the x-axis, we see a color ordering, which is a product of retardation. Retardation is the amount that the slower ray lags behind the faster ray. The interference colors that we see are a manifestation of this retardation. On the chart, we see that the interference colors range from first-order grays and oranges to second-order vivids, and then into third- and fourth-order pastels. On the y-axis, we have the thickness of the material in micrometers. The cross-cutting lines connect retardation and thickness to the corresponding birefringence. Here we have a grain mount in cross-polarized light. What we can see here is that interference colors increase in order from the grain boundary towards the center of the mineral. Take note that at the boundary you see first-order interference colors, which are the whites, oranges, and grays. Next, you see the second-order vivids, and as we proceed to the center of the mineral, you see the third and fourth-order muted vivids. Let's try an example together where we are calculating birefringence in a thin section. Here we start in plain polarized light, turn our analyzer on for cross-polarized light. Take a moment to observe the minerals in this thin section. Can you see that there are 2 main types of minerals here? The larger streaky grains are minerals characterized by significantly high retardation and interference colors. We will not be focusing on these grains. Instead, we will be focusing on the smaller grains that display low-order yellow and gray interference colors. First, we find that low-order gray interference color on our chart. We see that it plots here on the x-axis. Next, we need to see where it plots along the y-axis. Typical thin sections are around 30 micrometers thick. We find where 30 micrometers is on our graph and then trace it over to the gray interference color. Then, we follow that cross-cutting line up to the top of the graph where we get our value for birefringence. Here we see that the gray mineral had a value of 0.009, which is characteristically low. Here's another example from a thin section where all the minerals are the same. Focusing on the mineral grain in the center, we follow the interference colors progressing from the outside towards the center. Always use the highest order interference color that you see in determining birefringence for a given grain. This grain here plots here along the x-axis at a second-order blue. Our thickness is still at 30 micrometers, and when we follow the cross-cutting line to the top of the chart, we come up with a median birefringence value of 0.025. It is often okay to generalize your description as low, medium, high, or super high, as there is some variability in observed values. Here are some things to remember and some helpful tips. Be careful not to confuse opaque minerals with isotropic minerals. Opaque minerals never let light through, while isotropic minerals let plain polarized light through, but not cross-polarized light. Birefringence is most accurately calculated from the grain displaying the highest range in interference colors, extending outward from the center of the grain, and be wary of higher order interference colors, as they tend to be more pale.